We're going to continue to talk about operational amplifiers today. And so what we talked about last Friday, if my memory is serving me correctly, is just the basic skills needed to analyze an op-amp circuit. But that's probably the most boring thing that you could ever do with an op-amp, is just kind of see what it does. So instead, today, we're actually going to focus on applications of operational amplifiers, and we're going to look at the 6 most commonly used negative feedback op-amp topology. And I'll talk a little bit about how they're used and why they're used and all of that kind of good stuff. Okay. So let's call this lecture Common Op-Amp Topologies. And we are going to start with a circuit that you guys saw in your in-class assignment on last Friday. Okay. So our first example is going to look something like this. It's going to be drawn slightly differently. Aaron, are you muted? I'm hearing feedback over here. Thank you. So I'm starting with my basic op-amp. I'm going to choose to put the inverting input terminal on top and the non-inverting input terminal on bottom, like so. Here is my output terminal, and I'm going to apply my feedback path, like so. And I'm going to call this resistor, let's call it RF for feedback resistor. I'm going to place a resistor between the inverting input terminal and ground here. And I'm just going to call this resistance R1. And then I am going to apply some input voltage Vn here at the directly at the non-inverting input terminal. I am explicitly stating that this input voltage is a function of time, but it doesn't necessarily have to be. It's just really boring if it isn't, because we're just looking at basic simple DC circuit analysis with no real purpose. So I want you guys to consider this input signal to be really just any kind of voltage signal that you might be interested in. So this could be something like the output from an electric guitar pickup. It could be the output from a sensor that's measuring brain waves or something like that, okay? But really just any time varying voltage signal that we are interested in amplifying is what this Vn signal is representing. And then we're going to take our output voltage signal here at our output node, okay? And so our ultimate goal here is to analyze this generic circuit and understand how it behaves generically, so that if we ever see a circuit that's constructed like this, instead of bothering to do the analysis, we can identify, oh, this is an example of X amplifier. It behaves in this way, and we don't ever have to analyze it again because we know this is how it works. So that's kind of the modality that we're looking at today, okay? So to come up with those relationships for how this amplifier works, we are going to use that 5-step process that I talked about in our last class meeting. So let's start by saying that no current can flow into or out of our input terminals. Then I can see by inspection that the voltage that is present at the non-inverting input terminal with respect to ground is simply the input voltage I'm attempting to amplify. Applying op-amp rule number 2, that tells us that the voltage here at the inverting input terminal is also essentially our input voltage, Vn of t. And now I'm going to simply apply Kirchhoff's current law at the non-inverting input terminal, giving me the relationship that I will have Vn as a function of time divided by R1 plus Vn as a function of time minus Vout as a function of time divided by Rf is equal to 0. So if I were to rearrange this expression, putting all of my Vn terms on one side and my Vout term on the opposite side, what I would find is that the output voltage for this particular configuration is going to be equal to 1 plus my feedback resistance divided by my R1 resistance, and all of that is multiplied by my input signal. So this is an example of what's called a non-inverting amplifier. And it is a non-inverting amplifier because if my input signal, or let me put it this way, when my input signal is positive, my output signal is also positive. When my input signal is negative, my output signal is also negative. So effectively, this particular configuration keeps the phase of the input signal. Matthew.
So is that term the 1 plus RF over R1 are the
It is exactly that, and I will define that here in just a moment. Fantastic question, and you're 100% right, okay? So when we're dealing with an amplifier circuit, one of the most important characteristics of that amplifier is its voltage gain. So I'm going to define our closed loop voltage gain. So I have A for gain, V for voltage, and CL for closed loop. Another way to think about that is this is the amplifier's voltage with feedback taken into account because we have a feedback system here. And this is simply going to be the ratio of the output voltage divided by the input voltage. So another way to think about this closed loop voltage gain is it's kind of the transfer function of the system. It's describing what the amplifier is actually doing or how it processes an input signal, okay? And so in this case, our closed loop voltage gain is simply 1 plus that RF over R1 as Mr. Bearden surmised, right? So if we look at this closed loop voltage gain, we can see some interesting things, at least I think. So the smallest gain that this amplifier could ever provide is 1, okay? When this particular configuration is providing a voltage gain of 1, that's what we would call a unity gain buffer. Unity gain buffers are a very, very frequently used op-amp circuit in applications where the sensor that we are trying to take a signal out of is incapable of driving a load. So if we had something like a simple piezoelectric crystal or something like that, or maybe like a small scale pressure sensor that could generate a reasonable output voltage, but can't really supply any current, we might pass that signal through a unity gain buffer to use the power supplies for the op-amp to provide any current that is necessary to drive a connected load. So a unity gain buffer is a very, very common application of this particular topology, and it's actually a fundamental building block of what's called the instrumentation amplifier that is used in a lot of process and control systems. We're not going to talk about instrumentation amplifiers in this class because it's actually a combination of 3 different op-amps cascaded in a specific way, and we try to keep things down to a single op-amp in this class, but this is a building block for bigger and better op-amp related systems. Okay. So when RF is very small and R1 is very large, we have a unity gain buffer. Obviously, our closed loop voltage gain can obviously be much greater than 1 as well, if we want it to, when RF is much greater than R1, okay? So in a circuit like this, if we wanted to increase our overall voltage gain of our system, we could either increase the value of our feedback resistor or decrease the value of that R1 resistor. Okay. So just to recap things really quickly, this is our non-inverting amplifier. I want you to notice that the input signal is applied at the non-inverting input pin. Okay. So that's part of where the name comes from. The other part of the name is that the output signal has the same polarity as the input signal. And this is used whenever we simply want to essentially make signals either the same or larger. Okay. So to contrast that, let's look at an extremely similar circuit. The only thing that we are going to do here is we are going to swap the location of our input signal and ground. Okay. So this is the circuit that I'm dealing with now. Everything is going to be completely identical, except for two small changes, right? So here's my inverting input terminal, my non-inverting input terminal. Here's my output terminal. I'm going to have negative feedback. I will for all of these circuits. So here's my feedback resistor R sub F connected between my inverting input terminal and my output terminal. I'm going to have that same resistor R1 connected to the inverting input terminal as well. But now, instead of grounding the left-hand leg of this resistor, this is where I'm going to apply my input signal. And now I'm going to ground the non-inverting input node. So as we analyze this guy, we're going to take the exact same steps as we just did. Here's a 0 amp source, a 0 amps current flowing in, 0 amps current flowing into this guy. Our voltage present at our non-inverting input node is simply 0 volts, which means the voltage present at our inverting input node is also 0 volts. So we essentially have a virtual ground at the inverting input node. And applying KCL, I'm simply going to be adding these two currents together. So that's going to look like 0 minus Vn. So I'm going to write that as negative Vn divided by R1. And then I'll have plus 0 minus V out. So I'm just going to write that as minus V out divided by RF is equal to 0. And rearranging this expression slightly, we'll find that our output voltage is simply negative RF over R1 times our input voltage. And this means that our gain, AVCL, is simply negative RF over R1. So in this particular case, our input signal is applied through a resistive network on the inverting input side of our amplifier. And we can see that our output voltage has the negative sign or the negative polarity of our input voltage, meaning whenever our input voltage is a positive quantity, our output voltage is a negative quantity. And whenever our input voltage is a negative quantity, our output voltage is a positive quantity. So this is an example of an inverting amplifier. So let me put both of these circuits up at the same time so we can see very easily that they are literally the exact same circuit, except that we've swapped where ground was and we've swapped where VN was. Other than that, things are completely the same, okay? So in our non-inverting input amplifier, our voltage gain was constrained to be greater than or equal to 1. With our inverting amplifier, our voltage gain does not have that constraint. It's always going to be negative, but it can be less than 1, it could be greater than 1. It doesn't matter. It's established simply by the ratio of those two resistances, right? So for any resistor values, we can come up with any possible voltage gain we would ever want, including making our output signal smaller than our input signal or attenuating things if we were so inclined, okay? The drawback of this increased range on the voltage gain is that we're always going to get a negative output signal, okay? So typically speaking, you might take the output signal of this particular amplifier and run it through a second inverting amplifier with a gain of 1 to correct that back to a positive input signal if you wanted to. For a whole heck of a lot of applications, that negative sign is not going to remotely matter at all. Like it doesn't matter that the input signal and the output signal are 180 degrees out of phase. And so this particular topology right here is actually the most commonly used topology of all negative feedback op-amp circuits. As a matter of fact, when we get to the last two examples of what we're going to deal with in this class today, they're actually going to be this exact amplifier, except we're going to swap one of the resistors out with an energy storage element. So this is like the biggest fundamental building block of op-amp circuits. Any question about this inverting amplifier here? All right, so let's modify this guy slightly. So let's say that I have this circuit. Just starting with my basic op-amp. I'm applying my feedback path, some resistance RF. And then on the inverting input side, so between the inverting input node and what we have to the left, instead of having a single resistor, I'm going to put multiple resistors here. I'm going to derive this with 3, but we could realistically have more than 3 resistors here very easily. I'm going to call this resistor R1, and then over at this left-hand terminal, I'm going to apply a voltage V1 of t. I'll call this resistor R2, and then I'll apply some voltage V2 of t. This resistor will be R3, and I'll have some voltage V3 of t, like so. And now I'm going to simply ground this guy again. And my output signal is over here. So this is effectively the same inverting amplifier that we had from the previous example, except that now we've got multiple input signals connected through a resistive network on the inverting input side of the system, okay? So we're going to approach the analysis just like we've done with every other example. So let's say that this current is 0 amps and this current is 0 amps because of ideal op-amp rule number 1. This voltage is by inspection 0 volts, which means this voltage is also 0 volts. And now I'm going to write my KCL equation. So I'm going to add this current plus this current plus this current plus this current together. Those are all of the currents that are leaving the inverting input node. And what I'll find is that I should have negative V1 over R1 minus V2 over R2 minus V3 over R3 minus V out over RF is equal to 0. And if I rearrange this expression, I'll find that my output voltage V out of T is simply equal to negative RF times V1 over R1 plus V2 over R2 plus V3 over R3, and so on and so forth if I had multiple input signals. Okay. So what's this guy doing? Anybody have any thoughts? Matthew. So depends on what you mean by mixing the signals, but I will accept that answer. It is adding the signals together, but it's not adding them. So it's definitely adding the signals together, but each signal is being scaled by potentially a different amount, depending if R1, R2, and R3 are different from each other, right? So it's taking the voltage signal V1, scaling it by a factor of negative RF over R1, and then added to that is the voltage signal V2, scaled by a factor of negative RF over R2, and so on and so forth. So this is what's called a weighted inverting summer. It is a weighted inverting summer because each individual input signal is weighted or scaled by a different amount, okay? So this particular circuit and a few more are actually the reason why the operational amplifier has its name, operational amplifier. So what the op amp's real role is to perform mathematical operations on input signals. And this is how we perform the operation of addition. Now, we could, if we were so inclined, actually develop some sort of relationship for a weighted non-inverting summer where our input signals were placed on the non-inverting input side. But we would see if we did that example that the math gets real gross real fast for anything over 2 inputs. So this is the actual more common way to perform the operation of addition using an op amp. And then we would run the output of this amplifier into another inverting stage to correct it to be a positive quantity, because it's actually easier to design that system than it would be to design a system that can handle multiple input signals and keep everything positive the whole time. Okay. So if our signal R1 is equal to R2, or excuse me, is equal to R3, is just equal to, let's call it R in general, then our output voltage would reduce to negative RF over R multiplied by the simple sum of our input signals. Now, whether you guys realize it or not, you may not interact with this every day, but you've definitely seen it in your everyday lives. How many of you or your parents own a digital bathroom scale? Most of you, okay? So how a digital bathroom scale works, let me draw a really terrible picture of one. So mine at home looks something like this. I've got a big square, and then here's the place where I place my left foot, and here's the place where I place my right foot. And on both of these places, there is a load cell. I'm just going to put it in a black circle like this. So one for the heel of my foot, the other for the front of my foot, and that's the same on both sides, okay? So these are all just load cells, okay? And so what these load cells do is they convert the strain of me stepping on them into an electrical signal. Okay, so could be a simple thin film load cell. It might be a nickel strain gauge, depends on what size of load that you're measuring. But essentially, the change in the pressure that I'm applying to this load cell is generating some type of output voltage. And in this case, I have 4 output voltages, which I need to combine together to compute the overall weight on this digital scale. Well, that computation is performed by a an inverting summing amplifier, because all of the signals were going to be scaled by the exact same amount. And the ratio of those resistances is just whatever I need it to be to convert whatever the output signal of this guy is. So it might generate, let's say, 5 millivolts for every pound that load cell sees. And then I would use that ratio of resistances to scale that appropriately to a particular level. So the same principle is actually how the weigh stations that you see when you leave or enter a state work, just on a much, much larger scale. All of this is just a simple application of an op-amp circuit. Any other questions about this guy? I don't know that any of you actually asked a question, so I guess any questions about this guy before I move on to the next one? Okay. So we just figured out how to do addition. So let's figure out how to do subtraction. So let's say that I have the following op-amp circuit. This one is going to look a little bit more complicated, but we've actually seen an example similar to it in your in-class assignment from Friday, or at least a portion of it. So I'm going to have my feedback resistance, but instead of calling it RF this time, I'm going to call it R2 for reasons that will be obvious in a moment. Okay. Here's my output signal, V out as a function of time. Here's a resistance R1, and this is going to be an input signal, V1, as a function of time. And what I'm going to do on the non-inverting side is I'm going to put another resistor network, okay? So I might have a second resistor R2 here, and a second resistor R1 here. And I'm going to apply some second input signal, V2, on that leg of the bottom resistor R1, okay? So I have 2 different input signals. One is applied on the non-inverting side, and the other is applied on the inverting side, okay? So there are multiple different ways that we could potentially analyze this circuit, but I'm going to stick with that common 5-step process, okay? So I could observe that there's no current flowing into my input terminals. Now here's where things are going to get a little bit more difficult. I got to find out what the voltage is at this node. But remember, this is a nodal voltage. Our inverting input terminal voltage, our non-inverting input terminal voltage, and our output terminal voltages are all measured with respect to ground. So if I'm trying to find the voltage at that particular node, that is the same thing as me finding the voltage drop across that resistor R2, okay? So does anybody have any thoughts on how I might find the voltage drop across that resistor R2? So all KCL is going to tell us that the same current flows through R1 as flows from left to right through R1 as flows down through R2, which could be valuable because that means essentially that those 2 resistors are behaving as if they are in series. So I have a known voltage drop applied across 2 resistors in series, And I'm interested in finding the voltage only over the second resistor. So what could I do? Voltage division. Okay. So using voltage division, I would find that this voltage V plus is simply my input voltage V2 multiplied by a factor of R2 over R1 plus R2. Are we all okay with that application of voltage division there? That same voltage must show up at our inverting input node. So I can say that V minus is going to be equal to V2 times R2 over R1 plus R2. And now I would simply apply Kirchhoff's current law. So that KCL equation would look like V2 times R2 over R1 plus R2 minus V1. All of that is divided by R1. And then I would have plus V2 times R2 over R1 plus R2 minus V out and all of that is divided by R2. And I'm going to set this equal to 0. So I'm going to do something here that's going to make our lives a little bit easier, okay? So I'm going to multiply that factor of V1 by an R1 plus R2 over an R1 plus R2, okay? I'll explicitly write this out so that we can follow the math. So V2 times R2 over R1 plus R2 minus sorry, I wrote VI instead of V1. V1 times R1 plus R2 over R1 plus R2. All of this is divided by a factor of R1 plus that same V2 R2 over R1 plus R2 minus V out times R1 plus R2 over R1 plus R2 all over R2 is equal to 0. So I've done this so that I have a common denominator in my numerator, okay? So if I were to multiply both sides by a factor of R1 plus R2, essentially, I would be able to get rid of all of those denominators because it's common everywhere and I have 0 on the right-hand side, right? So that's going to look like V2 times R2 over R1 minus V1 times R1 plus R2 over R1 plus V2 times R2 over R2 is equal to V out times R1 plus R2 over R2. And so what I could do now is multiply through by the reciprocal of that R1 plus R2 over R2, right? So let me come over here so that we can just do the algebra out. So I would have V out is equal to V2 times R2 over R1 multiplied by R2 over R1 plus R2. I'm going to go ahead and add this second V2 term in. So plus V2 times R2 over R2 times R2 over R1 plus R2 minus V1 times R1 plus R2 over R1 times R2 over R1 plus R2. So let's do some simplifications here really quickly, okay? So I've got an R1 plus R2 divided by an R1 plus R2, so those guys cancel each other out pretty easily. This guy right here looks like R2 over R2, that's literally just 1. So they cancel each other out. So let's keep on manipulating this a little bit. So I've got V2 times, so R2 over R1 plus R2. And then I have 1 plus R2 over R1. Are we okay with that? Let's start there. So I have a common factor of V2 times R2 over R1 plus R2 in this term and this term, right? So if I factor that out, I'm left with 1 plus that R2 over R1. Okay. Well, what I'm going to do really quickly here is I'm going to change that factor of 1 into R1 over R1. So if I do R1 over R1 like so, I have R1 over R1 plus R2 over R1. Well, now I have a common denominator in that term, so I can actually put those guys together, and that's going to come out looking like R1 plus R2 divided by a factor of R1. And we can see that this guy cancels this guy. And now I have minus V1 times a factor of R2 over R1. And finally, sorry this took so many steps, we see that we actually have R2 divided by R1 multiplied by V2 minus V1 as our output voltage. So essentially, this particular circuit, let me scroll back up so we can see the damn thing, allows us to take the difference of those two input signals and then scale it by some common factor, right? So if all of the resistors were identical, then it would literally, the output would just be V2 minus V1. With these two pairs of max resistors, we can scale this difference by some value. So we could either make that difference larger or smaller if we were so inclined, okay? So this is how we perform the mathematical operation of subtraction using op amps. And we can also scale that difference signal as well if we were so inclined. Yes, Matthew.
Circuits like this to get and-
Yes, absolutely right. So these are all examples of analog signal processing, 100%. Now, analog computers, they use a lot more energy storage elements and all of that kind of stuff, but we're going to talk about that literally in our next two circuits. But yeah, you're 100% catching what I'm throwing. These are the fundamental building blocks of analog computing. As well as a lot of communication systems, control systems, and all that kind of good stuff too. Okay. So we did a whole hell of a lot of math here to come out with this relationship because I wanted to stick to this 5-step process for setting things up. We could have gotten that same result way faster just using superposition. Because if we use superposition, so if the the input signal V1 is on while the input signal V2 is off, we have an inverting amplifier. If we have the situation where V2 is on while V1 is off, we have a voltage divider being chained into a non-inverting amplifier. And then we would just sum those two outputs together and we would literally get that exact same result. So, all right. So we've talked about amplification and attenuation with our non-inverting and inverting amplifiers. We've done the mathematical operation of addition with our weighted inverting summer. We've done the mathematical operation of subtraction with our weighted, let me write this down, differencing amplifier. We can't do multiplication or division with a single op amp, so we'll have to leave those for later. So instead, we're going to jump to calculus. So we can actually do derivatives and integrals with single op amps. Carter. Make R2 and R1 the same. And it's now just the difference of the difference of the signals. Yeah. All right. So I legitimately can never remember which one is which for these. So I'm going to give them the names at the end and we're just going to figure out how they work. Okay. I'm going to draw these circuits using capacitors as the energy storage element. They could be implemented with inductors, but in most common applications, we use capacitors because the tolerance on a capacitor, like the manufacturing tolerance on a capacitor, is typically much tighter than the manufacturing tolerance on an inductor. And so it's just easier to use capacitors because you have to do a lot less external tuning to make sure that things work the way that we expect them to. Okay. So because we're going to be using capacitors for these circuits, I want to remind you of a couple of relationships that you already know, or at least should. So the first of those relationships is that the current flowing through a capacitor is simply the capacitance value times the derivative of the capacitor voltage with respect to time. And the inverse of this relationship is that the voltage drop across a capacitor is given by 1 over C times the integral from negative infinity to T of the capacitor current with respect to time. And I'm choosing to deal with the integral from negative infinity to T specifically so that I don't have to bother with the initial condition on the capacitor, which will just make the math harder. Okay. So let's start with this circuit right here. So I've drawn my simple op amp. For this first circuit, I am going to put a resistor in the feedback position. So this will be RF. And instead of putting another resistor in, I'm going to place a capacitor here, C. Okay. I'm going to apply my input voltage on the left-hand leg of this capacitor. I'm going to take my output voltage at the output terminal of the op amp, and I am simply going to ground my non-inverting input node. Okay. So before we get into applying our op amp rules and all of that kind of stuff, I just want to characterize the capacitor really quickly. So I'm going to say that the voltage drop across my capacitor is going to have the positive polarity terminal on the left, and the current flowing through my capacitor is going to be defined as flowing into the positive polarity terminal of that voltage VC. And we are largely going to be able to just do that 5-step process and figure out how this guy behaves, even though we have calculus-based relationships to deal with, okay? So let's start by saying that we have 0 amps of current here and 0 amps of current here. Our voltage at our non-inverting input node is 0 volts. And the voltage at the inverting input node is also 0 volts. And I'm going to do my KCL slightly differently here. I'm going to say that this current flowing in needs to equal to this current flowing out. Okay. So it's still KCL. I'm just getting the signs in a way that I want them. Okay. So if I write that KCL relationship down, I would simply have my capacitor current, IC of t, is equal to 0 minus V out. So let's call that negative V out divided by RF. And so now I'm just going to rearrange this relationship. So that would mean that I would have V out is equal to negative RF times IC. Well, we know that our capacitor current is related to our capacitor voltage. So I could take this one step further, and I could say that this is negative RF times C times the derivative of my capacitor voltage with respect to time. And so now what I need to figure out is how my capacitor voltage is related to my input voltage. To make this a little bit easier on you guys, I'm going to modify my circuit slightly. Instead of just saying I have that voltage applied to that pin, I'm going to explicitly include a voltage source here, right? So there's our Vn of t. We can see that the positive polarity terminal of our input voltage is at the same node as the positive polarity terminal of our capacitor voltage. The negative polarity terminal of our input voltage is at ground, and the negative polarity terminal of VC is at 0 volts or a virtual ground. So essentially, our input voltage is the exact same thing as our capacitor voltage. Is everybody okay with that? So positive polarity terminals are at the same node, negative polarity terminals are both at ground. So it's the same voltage. So that means I could actually write this as negative RF times C times the derivative of my input voltage with respect to ground. So this is an example of a differentiating amplifier from an analog signal processing standpoint. We commonly refer to it as an active low-pass filter in communication systems. And this is a differentiating block in control systems. So this particular amplifier configuration right here is used all throughout multiple different aspects of electrical engineering. Behaves the exact same way essentially every time, but it plays different roles in different systems. We'll talk about filtering a little bit once we get to the concept of impedance, once we deal with AC circuits, which is our next topic. So, does anybody have any questions about this guy before I show you how the integrating amplifiers work? All right, so the only thing I'm going to do now is I'm going to take this exact same circuit and I'm just going to switch where R and C are placed. So I have some feedback capacitance here, CF. Here's my output voltage. Here's my resistance R. Here's my input voltage. And I'm going to ground this node. Let's define the voltage drop across the capacitor as, once again, positive polarity on the left. And let's define our current, once again, as flowing into the positive polarity terminal, like so. Okay. All right, so the derivation for this guy is a little bit harder, but it's not particularly crazy, okay? So we know that we have 0 amps of current flowing into our input nodes. We can see very easily that the voltage present at our non-inverting input node is 0 amps, which means the voltage present at our inverting input node must also be 0 volts. Sorry, I think I said 0 amps a moment ago, but it's obviously volts. And so what I'm going to do now is I'm going to perform KCL, where I'm going to say that this current flowing in is equal to this current flowing out yet again. Okay. So that's going to give me the relationship V in as a function of time divided by R is equal to IC. Now, it's a little bit difficult for us to figure out what to do next. So I'm just going to kind of spell it out, okay? So in the last example, we had to figure out how our capacitor voltage was related to our input voltage. In this guy, we actually have to figure out how our capacitor voltage is related to our output voltage and then go from there, okay? Since our capacitor is connected directly to the output node in this case, and our capacitor was connected directly to our input node in the prior example. So do any of you guys have any thoughts on how VC and Vout are related to each other? And once again, I'll draw things out a little bit better that might help you see it, okay? So I would put the positive polarity terminal of Vout here, the negative polarity terminal there. And so this could be how we could represent Vout as a function of time. So to me, I see that the positive polarity terminal of Vout is at the output node, and the negative polarity terminal of VC is at the output node. I see that the negative polarity terminal of Vout is at ground, and the positive polarity terminal of VC is at ground. So to me, that means that these two voltages are equal and opposite to each other because they have the opposite polarity, right? Positive and negative are connected together on both sides. So if we observe that V out is equal to VC. We could take this one step further by saying that VC is equal to 1 over C times the integral from negative infinity to T of IC dt. And now we can substitute in our relationship for IC that we got by applying Kirchhoff's current law. And so that's going to look like 1 over C times the integral from negative infinity to T of Vn divided by R and pulling that factor of R out. Sorry, those C should be CFs. We're going to get 1 over R times CF times the integral from negative infinity to T of, sorry, Vn with respect to time. So this particular configuration integrates our input signal and then scales it by a factor of 1 over RC, where our previous example differentiated our input signal and scaled it by a factor of RF times RC. Okay. So this is an integrating amplifier. From an analog signal processing standpoint, it is a high pass filter, if I'm remembering correctly, from the communication system standpoint, and it is an integrating block in controls systems engineering.